Okay, great. With that introduction behind us, we're ready to try our hand at pre-processing data from a single cell experiment. And up to this point in the course, we've been working with a bulk RNA-seq experiment. And so, unfortunately, it's time to say goodbye to our beloved course data set. It has served us well. We've learned a lot about RNA-seq data analysis and hopefully learned a thing or two about this interesting and important neglected tropical disease called leishmaniasis. So if we're not going to use the Leishmania data set for today's lecture, what will we use? Well, if we turn our attention back to the lecture page, I've provided a link here for you to download a new set of raw FASTQ files. Don't fret, these are relatively small. They're much smaller than the course data set. They'll take up about 5 gigs of storage space on your hard drive. So go ahead, if you haven't done so already, please download those files, but please do not uncompress them. So same as before, just leave your raw FASTQ files as fastq.gz or gzipped files. And this data is from 1,000 peripheral blood mononuclear cells, or PBMCs. And it's actually one of the example data sets that 10x provides on their data page, which I've linked to here. Now, I've done some minimal just kind of merging of different lane files here to make this simple and have it represented as just 2 FASTQ files that you download. Remember, 2 FASTQ files because we have a set of forward reads that captures that barcode and UMI, and then a reverse read to actually get the transcript. I also think PBMCs make sense as a really logical place to start working with single cell data because we know a lot about PBMCs. We know what cell types are present in the blood, and so it gives us some ground truth to hold on to as we work our way through an analysis. We have some expectation then of what kinds of cells and clusters we should see in our data if we're doing the analysis properly. In addition to these raw FASTQ files, you need a human transcriptome reference index file. You're in luck. This is exactly the same index file that we used and in fact created in lecture 2 when we did our read mapping. So you can use this file again. If you happen to just delete that file after lecture 2, or maybe you can't find that file anymore, no worries. It's easy and in fact good practice to just regenerate this file. You would do that just by going to Ensemble, getting that human reference transcriptome FASTA file, and then using Callisto's index function. And this has nothing to do with Callisto bus tools. Just use the plain old Callisto and the index function to create an index from that FASTA file. We also need a transcript to gene, or T2G, mapping file that tells us which transcripts are associated with which genes. That file is easy to generate as well, and we'll generate that in Callisto bus tools rather than just Callisto. But for the sake of simplicity and just keeping things moving along in this lecture, I've actually just provided that for you to download directly. But I will show you how to make it yourself just so you're aware of how to do this with your own data. And then last but certainly not least, we need Callisto bus tools, and we'll use this particular implementation of Callisto bus tools called KB Python that has a Python wrapper around a lot of these tools. You're in luck. You already hopefully have this installed. If you remember from way back in lecture 1 when we talked about setting up Conda environments and installing software and the dependencies for those pieces of software into those environments, KB Python was one of the things that we installed. So we had 4 Conda environments. We had 1 general RNA-seq one with Callisto and some other QC tools. We had a couple environments that had metagenomic analysis software that we used to fish through or mine our RNA-seq data for potential microbes. And then we had this other environment we hadn't used up to this point in the course, and now it's time to use it. And so if you don't have that environment set up, or if you're not sure if you do, don't worry, you can head back to our Conda protocol on the protocols page, and it walks you through how to get all of these and catch up quickly. If for some reason you can't get KB Python installed or you can't get it to work, don't worry. Everything I'll do today, I'll provide you the output from KB, which you'll be able to use in R directly in the next lecture. So if you can't get this working, just still follow along with this lecture so you understand the concepts. In case it's not immediately obvious, for this portion of the lecture, we're going to be working in the terminal. We're going to be entering commands at the command prompt. we're not working in R. And so the way, if you recall, that we work with these Conda environments is first we have to activate the environment, and we do that with Conda, activate, and the name of the environment. I called this environment KB, maybe you did too. And then we call the program once we have that environment activated, and it just so happens that the program has the same name as the environment, so we just call on KB. Once we do that, a handy way to just check, and something I encourage you to do, is just to type KB and then --list. So that list option will tell you all of the supported single cell technologies that Callisto bus tools can work with. And when you type that, which we'll do in just a minute, you should get an output that looks something like this. It's a table. It tells you that this is a list of supported single cell technologies, and you see the name of the technology on the left-hand side. So you can see all version 1, 2, and 3 of 10x Genomics is supported, as are CellSeq, DropSeq, InDrop, and others. And one thing I just want to point your attention to is that for some of these technologies, and in fact all of the 10x technologies, there is something called a whitelist included in the software. Now, we're not going to talk about whitelists in any great detail, but suffice it to say, these whitelists contain all of the possible barcodes in the assays that are supported on these technology platforms. And so it's critical to have a whitelist because it lets us do that very first part of our processing, which is to look through our FASTQ files and figure out which reads go with which droplet or cell. And lucky for us, Callisto Bus Tools includes the whitelist for these different technology versions in the software itself, so we don't have to go looking for them. Okay, so I really won't talk anymore about whitelists except to say we've got what we need inside of the software for today. Okay, so what I'll do now is head over to my terminal, and I'm going to do exactly what I just described on the slides. I'm going to type KB, Conda activate KB. When I do that, I can see I changed from base to KB. And so now I can type KB --list, and indeed I can see that full list of supported tools exactly as I just showed you in the previous slide. Okay, so we're ready to go. I've activated the Conda environment. I know that I have KB installed. I know that I'm working with a piece of software that supports the technology that I'm about to try to analyze. And so now we have to make sure we have the right input files. So that's the data you get from the course website, or that you already have from previous work in the course. 2 FASTQ files, okay? Both of them should be labeled PBMC 1K for 1,000 cells, V3 for 10x version 3. And then I've merged the lanes so that we just have the forward reads and the reverse reads. Now, remember, those forward reads are pretty short. They just need to capture the barcode and the UMI. So it's no surprise that our reverse reads, which are much longer, represent a much larger file than the forward reads. So that's expected. That's a good thing. In bulk RNA-seq, if we had paired-in sequencing, it would be unusual and perhaps problematic if these files were a different size. There's our transcript to gene mapping file, which again, I made available for you to download, but in just a minute, I'm going to show you how to make it yourself. And then there's that index file that we had from lecture 2, which hopefully you either have already or can generate again. Okay, I'm heading back to the slides just to highlight how we can actually work with KB Python in the command line to generate what we need to do. And I just want to highlight here, you do not need to run this code. I already provide the transcript of gene text file in the downloads for this lecture. It won't hurt you to run this code, but it'll take some time, and I'm trying to save you that time. So how do you generate your own transcript to gene mapping file? You do that with kbref. And I'm showing you the breakdown of the code you would enter in the command line here, just as I did before in the past for Callisto. And so we have calling the program and the function. This is, of course, assuming you've activated the Conda environment. We have our little slash here that indicates that the code continues on the next line. We then download a pre-built index. So Callisto Bus Tools actually lets you already fetch a pre-built index that they've prepared if you're working with human or mouse, and you do that using the -d for download command. We then tell it the path or the name, of the index file that we want to create, or where we want to store this thing that it downloaded. And so for us, we want that path to be in our working directory, so we don't have to specify anything else other than the name, and we're going to have it call it this. And then we want to create the path or name of the transcript to gene mapping file to be created. And so that's going to end up, again, in our working directory, and it's going to be called transcript to gene.txt. So this transcript to gene mapping file will be created from this index. Okay, great. So now that we have that, we're ready to go. And ready to go here means that we're ready to actually pre-process our raw FASTQ files. We do that using kb count. So we call on the program again, and we use the count instead of the reference function. We provide it with the list of FASTQ files, a forward FASTQ file, space, and a reverse FASTQ file. We provide it with the path for the reference index. That's the one you have from way back in lecture 2. We tell it what technology was used to generate this data. In the case of the data we're using today for the 1000 PBMCs, this is 10x version 3. We tell it where the transcript to gene mapping file can be found. It's in my working directory, so the path is just the name. How many threads we want to use? I have four CPU cores, so I can use 8 threads. And then we tell it, and this is really important, that we want it to convert the counts to a Cell Ranger compatible format, so that when we do all this pre-processing, what we will end up with in the end will be text files that resemble what you would get out of Cell Ranger. That's going to make it easier for us to work with downstream tools once we're done with this pre-processing. Okay, so now that we've done that, we're ready to actually give this a try ourselves. I'm going to head back over to the terminal. I'm going to just copy and paste this code directly into the terminal. I need to make sure that I'm actually in my working directory. So I've called that directory DIY single cell RNA-seq. I'm not working in the course dataset directory that we've used up to this point in the course. It's too complex, got other stuff in there. I just started a clean slate here. I just have my files and everything else. I'm ready to go. So I'm going to drag this down. It'll open a new terminal window. That's fine. I can zoom in a little bit here so you can see that. I can activate KB again. And I can paste in what I'm going to do here, which is KB count. I need to actually put in the names of my FASTQ files. Not these dummy names that were filling the space here. And I know that the reverse file name is the same, just with R2 instead of R1. So I can just make that tiny edit. Everything else looks good. KB count, my read 1, read 2, the index, which it sees here in the directory, the version 3 chemistry, and transcript to gene mapping file, which is there, 8 threads, and I want a Cell Ranger compatible output, and I'm going to go. Now, immediately it creates a temporary output directory, and it started to process and move through that data. Okay, we're going to give it just a minute to do what it needs to do, and we'll be back in just a second. All right, the pre-processing is now done. For me, on my laptop, that took about 10 minutes, less than 10 minutes, maybe closer to 6 or 7 minutes to work through those 1000 PBMCs. And you can see Callisto Bus Tools, recognizing the index, finding the FASTQ files, creating those barcode UMI set files or bus files, seeing that the whitelist wasn't provided, so copying a prepackaged whitelist, and then moving through the process of preparing and sorting the bus file, and then using that bus file to generate a count matrix. If I head over to the working directory that I'm working in, I now see that I have a lot more here. more than just my original FASTQ files and that transcript to gene mapping file and the index. Those were the 4 original files in that folder. Now I see a bus file, and those bus files have been used to generate counts, an unfiltered counts folder, which inside contains a Cell Ranger compatible set of output files, including barcodes, an expression matrix, and more. It's this counts unfiltered folder that we're going to use moving forward and import into R and work with in R. You could get rid of the remainder of these files if you'd like. However, we're going to keep these JSON files. These are log files that tell us about how KB performed on this data set and some metrics that we'll use to generate a quality control report in the next part of the lecture. That's it.